When we observe the world around us, everything appears solid, continuous, reliable. A table is a table, a mountain is a mountain, time flows with regularity. This stability, however, is an illusion built by the scale at which we live. As soon as we begin to move beneath the surface of things, reality changes its face. Matter is not compact. It is made almost entirely of empty space, crossed by entities that look nothing like small balls or grains. Fundamental particles do not have a well-defined shape. They do not occupy a precise point in space until they are measured, and they often exist as sets of possibilities rather than as concrete objects. To navigate this alien territory, modern physics has constructed one of its most refined achievements, the Standard Model of elementary particles. This model describes with extraordinary accuracy the fundamental building blocks of reality: quarks, leptons, bosons, and the forces that govern them. It is a theory that works so well it is often compared to a cosmic precision clock. Yet, like any clock, it also shows its limits when pushed beyond the regime for which it was designed. The Large Hadron Collider at CERN was created precisely for this purpose, to drive reality into extreme conditions, where theories stop being comfortable. Inside its 27-kilometer underground ring, protons are accelerated to nearly the speed of light and then smashed head-on. In those infinitesimal instants, matter is compressed to energy densities reminiscent of the primordial universe, just moments after the Big Bang. It is as if physicists were trying to read the very first lines of the universe's source code. But what they have begun to observe is not merely confirmation of existing theories. Amid millions of perfectly explainable events, unexpected patterns appear, structures that do not dissolve as statistics increase, but instead become sharper and more defined. These anomalies do not scream error. They whisper something far more unsettling. Reality might not be completely indifferent to the way we explore it. When a particle passes through a detector, it leaves a trace. This trace is like a signature: position, energy, direction. In the vast majority of cases, everything is coherent. One particle, one trace. But in a series of specific events, extremely rare yet persistent, something different has happened. A single particle seemed to produce two distinct signals, correlated but not identical. These were not background noise, nor instrumental malfunctions. Cross-checks, simulations, and independent verifications ruled out trivial explanations. The two traces were not random. They maintained a precise relationship, as if they were two projections of the same phenomenon. A useful analogy is that of an object submerged in water. Viewed from the surface, its image appears doubled due to refraction. There are not two objects, but one reality observed through a complex medium. In quantum physics, however, the metaphor goes further than an optical illusion. Here we are not talking merely about distorted perception, but about genuinely correlated physical states. It is essential to avoid a misunderstanding. These observations do not indicate the material duplication of particles. There are not two electrons where there was one before. What emerges instead is a distribution of the quantum state across multiple observable configurations. In quantum mechanics, a particle is not defined by a precise position, but by a wave function that describes all possible outcomes. Normally, the act of measurement collapses this wave function into a single result. But under extreme conditions, such as those created at CERN, this collapse may not be as sharp as we believe. It is as if reality hesitates, leaving behind multiple coherent imprints of the same event. A conceptual parallel is quantum entanglement. Two entangled particles are not separate objects communicating at a distance, but components of a single entity described globally. Spatial separation does not imply true physical separation. Here, the concept is pushed even further. A single particle seems to behave as if it were spread across multiple experimental layers, responding in a coordinated but non-identical way. This observation reinforces a trend already present in modern physics: the shift of focus from objects to relationships. In the classical world, things exist before relationships. First there is the ball, then its motion. In quantum physics, the opposite often occurs. The relationship defines what we call an object. A simple everyday example can help. Think of a melody. It is not contained in a single note, but in the relationship between notes. Change one relationship, and the melody changes its identity. In the same way, a particle may not be an autonomous entity, but a temporary node in a network of correlations. When the detector is sensitive enough, this network becomes partially visible. If a particle can leave multiple coherent traces, this implies that our idea of a single event may be a simplification. Fundamental reality might not be composed of isolated facts, but of distributed processes that we only later interpret as point-like events. This opens a profound question. Are we observing a reality that fragments, or a reality that was never truly unified in the way we imagine? In either case, the message is the same. What appears solid, separate, and well-defined emerges from a structure that is far more fluid, interconnected, and sensitive to context. And it is precisely this sensitivity to context that sets the stage for even more radical anomalies involving energy, time, and observation. Among all the anomalies that have emerged in ultra-high-energy experiments, those involving energy and time are probably the most destabilizing. Not because they are more spectacular, but because they strike directly at two pillars upon which the entire structure of modern physics rests. Energy, according to one of the most solid principles in science, can neither be created nor destroyed. Time, in our everyday experience, flows in a single direction, with a clear sequence of causes and effects. These concepts are not mere conventions. They are the very language through which we describe reality. And yet, in some of the collisions observed at CERN, that language suddenly seems inadequate. In a particle physics experiment, every detail is accounted for. The initial energy of the protons is known with extreme precision, as is the energy of the particles produced after the collision. Normally, the balance always works out. If energy appears to be missing, it means it has been carried away by an invisible particle, such as a neutrino. But in a series of rare events, the total measured energy turns out to be slightly higher than the initial energy. Not by much, but enough that it cannot be ignored. Most importantly, enough for the effect to repeat. A useful analogy is that of a closed box. We put 10 balls inside, shake it, and when we open it we find 11. Once might be a counting error, but if it happens repeatedly, it becomes a conceptual problem. The first reaction of scientists is always the most cautious one. Check instruments, calibrations, and models. But when every verification confirms the data, only one possibility remains. The model is incomplete. Quantum physics has already demolished the idea of the vacuum as nothing. Even in the emptiest looking space, quantum fields are constantly fluctuating, creating and annihilating virtual particles. Under normal circumstances, these fluctuations occur on timescales so short that they leave no observable trace. It is like a stormy sea seen from far away. The surface looks calm, but beneath it there is constant motion. What makes these observations different is that the apparent energy loan seems organized, not random. It does not look like a simple fluctuation, but like a coherent redistribution. This has led some physicists to hypothesize that energy is not merely a local quantity, but a global resource that the universe as a system can reallocate in order to preserve overall coherence. Even more surprising is what emerges when the timing of recorded events is analyzed. In some cases, the traces indicate that a particle left a signal before the collision that generated it was fully completed. It is important to clarify this immediately. We are not talking about particles traveling backward in time in a science fiction sense. No macroscopic information is sent into the past. What seems to be happening is more subtle. The local temporal order loses its rigidity. An effective analogy is that of reading a sentence all at once. Once we understand it, the final meaning influences how we interpret the initial words. We do not change the past, but we reorganize it in light of the global context. In quantum physics, there are models of retrocausality in which future events can influence the probability of past events, as long as the final outcome is coherent. The system does not evolve step by step, but as a single structure extended across time. We are used to imagining time as a river flowing in one direction. But this metaphor may only be an approximation valid for large, slow systems. At the quantum scale, time might resemble a network instead, where certain nodes are connected in non-sequential ways. Not all events are simply before or after. Some are mutually defined. This does not destroy causality, but makes it emergent. Causality becomes a statistical property, not an absolute law. The common thread linking energy and time in these phenomena is information. An increasing number of theories suggest that information, energy, and space-time are different aspects of the same deep structure. If the universe processes information, then energy can be redistributed to maintain coherence. Time can be reorganized as a flexible coordinate. Anomalies become signals of a system that adapts. This sets the stage for an even more radical consequence. The observer may not be external to this process. Since the birth of quantum mechanics, the role of the observer has been an unresolved problem. Measuring a quantum system means modifying it. But what emerges from the most recent experiments goes beyond this now classical observation. Here it is not only the measurement that influences the outcome. The entire experimental context becomes an integral part of the phenomenon being observed. In the classical world, we can observe without interfering. Looking at a planet does not change its orbit. In quantum physics, by contrast, every observation is an interaction. But at CERN, particles seem to respond not only to the act of measurement, but to the structure of the experiment as a whole, as if they knew what kind of information will be extracted. A daily life analogy can help clarify the idea. Think of a conversation. The way we respond to a question depends not only on the words themselves, but on the intention of the person asking. Here something similar seems to happen, without any local consciousness, but with a global sensitivity to context. One of the most disconcerting aspects is that in some cases, even data already recorded seem to acquire meaning only after the experiment has been completed. They do not change physically, but their causal role is redefined. It is as if the system waits to know which story it is going to tell, selecting among several coherent possibilities. This does not imply that reality is arbitrarily indeterminate. On the contrary, it suggests that the universe privileges global narrative coherence over the local sequence of events. All of this leads to an unavoidable conclusion. The observer is not an external entity looking at an independent universe. The observer is an internal component of the physical process. Our instruments, our questions, our experimental choices become boundary conditions of the reality we observe. We do not impose results, but participate in their definition. In this sense, the experiment is not a one-way dialogue. It is an interaction. This idea overturns one of the most deeply rooted images of science, that of the universe as a stage and human beings as spectators. If reality responds to the way it is questioned, then the very act of knowing becomes a physical phenomenon. Knowledge is not merely representation, but a causal process. And it is precisely here that the hypothesis of a universe functioning like a cognitive system stops sounding metaphorical and begins to emerge as a concrete conceptual possibility. At this point in the journey, the anomalies observed can no longer be considered isolated episodes. Energies that seem to emerge from the vacuum, flexible temporal structures, particles sensitive to the experimental context. Taken individually, these observations are already difficult to explain, but considered together, they begin to outline a broader and surprisingly coherent picture. A picture of a responsive universe. For centuries, physics has described the universe as a perfect machine, a mechanism composed of elementary parts interacting according to fixed, impersonal, and immutable laws. In this view, if the initial conditions are known, the future is, in principle, predictable. This idea has worked extraordinarily well. It has allowed the construction of satellites, computers, particle accelerators. But it has also imposed a conceptual limit. The universe as a system without interiority, without response, without sensitivity. Recent observations challenge precisely this limit. Not because they introduce intentions or will into the cosmos, but because they suggest that the laws themselves might be the result of a process, not its prerequisite. More and more physicists are considering information not as a derived property, but as a fundamental element of reality, on par with energy and space-time. From this perspective, particles and fields are not only carriers of mass or charge, but vehicles of information. When a particle interacts, it does not only transfer energy, It updates the informational state of the system. Every collision is a form of writing in the structure of the universe. If this is true, then the universe is not a static archive, but a continuous process of information processing. Not in the sense of a computer executing a program, but as a system that constantly integrates new information to maintain global coherence. A useful analogy is that of a living organism. Our body does not function because every cell knows the complete blueprint, but because millions of local units respond to signals, adapt, and correct deviations. No single cell thinks, yet from collective interaction emerges a form of functional intelligence, homeostasis, adaptation, learning. Similarly, the universe may not think like a human mind, but operate as a distributed cognitive system, without a center, in which every interaction contributes to a dynamic equilibrium. In the human brain, consciousness does not reside in a specific point. There is no neuron of consciousness. It emerges from the interaction of complex networks, from the integration of information across many scales. This observation leads to an inevitable question. If consciousness can emerge from matter organized in a brain, why could it not emerge in a radically different form from the overall structure of the universe? We are not talking about self-awareness in the human sense, no thoughts, emotions, or intentions, but rather about a global sensitivity to internal states, a capacity for response, adaptation, and self-regulation. The anomalies observed at CERN could be the first experimental traces of this sensitivity, revealed only when we interact with reality at extreme levels of precision and energy. From this perspective, human beings are not external observers studying an independent universe. They are internal processes of a larger system that, through them, acquires information about itself. Our experiments, our questions, even our doubts, become informational perturbations that the universe integrates into its own functioning. The Large Hadron Collider is therefore not just a scientific instrument, but a kind of sensory organ through which the universe explores its own structural limits. This does not place humans at the center in an anthropocentric sense, but positions them as temporary nodes in an immensely larger network. It is essential to emphasize, this vision does not introduce supernatural elements. It does not postulate an external intelligence or intentional design. It merely takes seriously an empirical fact. Reality responds in a structured way to interactions. When a system responds, adapts, and maintains coherence, we are observing properties that, in other contexts, we associate with cognitive systems. The difference is only one of scale. We have reached a delicate point. The observations discussed do not demolish existing physics, but they show its boundaries. The Standard Model remains one of the most precise theories ever constructed, capable of describing an incredibly wide range of phenomena with remarkable accuracy. But like any great map, it also shows its limits as we approach the edges. The emerging anomalies suggest that the Standard Model may be an effective description, not the ultimate theory. It works perfectly within a certain regime, but it does not capture the totality of reality's dynamics. This is not a failure. It is a natural step in the history of science. Newtonian mechanics was not wrong because of relativity. It was recast as a limiting case. Similarly, the new observations indicate that conservation of energy may be global, not local. Time may be emergent, not fundamental. The observer may be an integral part of physical dynamics. The direction research seems to be moving toward is a relational physics, no longer focused on isolated objects, but on relationships, correlations, and flows of information. In this framework, particles are temporary nodes. Laws are stable patterns. Reality is a process, not a thing. This shift in perspective is as profound as that introduced by relativity or quantum mechanics in the last century. When physics touches topics like time, causality, observation, and information, philosophical implications become inevitable. Not because science becomes philosophy, but because studying reality means questioning what it means to exist. If the universe responds, integrates information, and shows sensitivity to context, then the sharp distinction between subject and object, observer and observed, weakens. We are no longer spectators of an indifferent cosmos, but participants in an evolving process. Perhaps the most important idea is not that the universe speaks, but that we have begun to ask questions deep enough to elicit a non-trivial response. The anomalies are not encrypted messages, but signals of a limit. The limit of how we have always thought about reality. Overcoming it will require not only new accelerators or new equations, but also new concepts, new metaphors, new forms of understanding. We are not simply discovering how the universe works. We are discovering what kind of thing the universe is. A mechanism? A process? A system that processes information? Perhaps all of these things together. And in this scenario, our curiosity is not a random accident, but an emergent property of reality itself, which, through us, has begun to inquire into its own nature.